So we're going to start with Adrian from Things Industry. Adrian has been working for 4 years with TTN. Is head of engineering, which means that, among other things, is responsible for the development of the network server of TTI and also its operation. So he's going to recap, introduce LoRaWAN, and then explain how to onboard easily an end device and how to track the network operations. So, Adrian.
Hello, everyone, and thank you for having me today. My name is Adrian-Stefan Mares, and I've already been introduced. I'm head of engineering at the Things Industries. I handle, as was said, operations and development there. I lead our team, which builds a product, which is called the LoRaWAN stack, our network server stack. Today, I'm going to be talking a bit about building end-to-end LoRaWAN solutions. The talk itself is introductory. It assumes no prior knowledge of LoRaWAN. It introduces a bit LoRaWAN and what you should be expecting while you use LoRaWAN. And it's going to make you comfortable with the components of the LoRaWAN ecosystem. That's the target here. And by the end, I hope that we will touch every end of an end-to-end solution. So a bit on the Things. So I represent the Things Industries and the Things Network. The Things Network is a public LoRaWAN network which is targeted at developers. The spirit behind the Things Network is let's build this thing together. People add coverage to the network, and in turn they get to use their end devices to develop proof of concepts, to actually develop LoRaWAN further, and to have extra information. A bit more on the LoRaWAN topology outside of the things. So in a typical LoRaWAN network, we have a number of components. On the most left-hand side, in this case here, we have the end devices. The end devices themselves are the bread and butter of LoRaWAN. They are constrained, low power, generally even battery-powered end devices that do certain actions. Most of them are sensors. You can think of them like water sensors or temperature. In general, they collect data, they collect telemetry, but they can also be actuators. Think of a remotely controlled valve, for example, maybe some street lights, and there are many use cases that you can build. Communication is going in both directions in LoRaWAN. Now, next to all of these end devices, which can be in the orders of tens of thousands, hundreds of thousands, we have gateways, which are an order of magnitude a bit less. They are passive components of the LoRaWAN ecosystem. They collect the messages from the air, and they forward it via over IP back to the network server. Now, this is a bit different to how IoT is done in other ecosystems, because you are used to directly communicating with the end platform. But we do this in LoRaWAN in order to reduce the footprint that we have to put on the end device. So the end device is low power. We want to do as little computation as possible, to use as little materials as possible. And in order to do that, we move the complexity in this middle layer, which is the LoRaWAN network server. Once a packet has been received by a gateway, it is passed over IP to the LoRaWAN network server, and the LoRaWAN network server does a series of processing steps. First of all, we want to deduplicate the packet. So we want to check which end device has sent it, how many times we have received it. We want to collect some information. Maybe we want to ask the device to use less power while transmitting or more power while transmitting in order to optimize battery usage. And finally, after we've done this intermediate step, we can actually pass the telemetry, the state that we got from the end device, to an application, to your day-to-day data collection platform, data lake, any sort of processing that you have in mind, usually dashboards. The idea is that in order to lower the footprint, the amount of information that we have to store on the end device, we don't really have a negotiation step. You are used to, when you receive an IoT device, to have to onboard it with the platform. The end device connects to the platform, and it sort of registers itself. In LoRaWAN, that is something that you do out of band. So you pre-register the end device on the network server, and you can then start communication. Now, LoRaWAN itself, since it uses radio, it's a protocol which requires encryption. In this case, in LoRaWAN, we have symmetric encryption. So there is a session key which is shared between the end device and the LoRa network server. The session key itself ensures that even though you may hear the packet over the air, no one else can actually look what's inside of it. And in order to derive this key, to have this session key that is used during communication, we use a component that's called the join server. I'll go back there. Sorry. The join server serves a very important role in the LoRaWAN ecosystem. It ensures that root keys, the keys which are used to derive the keys that we use during a communication session, are stored safely. The idea is that only the end device knows those keys, those root keys, and the manufacturer and the join server exchange them. The root keys never leave those two places. They are safely stored in enterprise management solutions. And in this way, we can ensure that even if we have to move the end device between networks, the new network cannot read the previous traffic, and the new network cannot read the old traffic either. It also authenticates the network components such that you can say only this particular network can communicate with my end device. And in general, it's recommended for all deployments. It is very important for security reasons. Now, back on the constrained devices subject, I was talking a lot about the fact that we would like to use as little power as possible and to have long battery lifetimes, to have small bills of materials. In the end, since we have high volumes of end devices, we would like the cost per end device to be as low as possible. In LoRa, and specifically LoRaWAN in our case, the payload, what you can send in a single message is constrained. It's between 50 bytes and around 240 bytes, depending on how good you can hear the end device. And this is different from what you may be used in other IoT technologies. In other IoT technologies, you can send as much data as you want very often, but here we are constrained a bit by the fact that we have low battery power over very high range in the order of kilometers. There are also some region-specific rules that we have to abide to. So for example, in the European regions, we have this concept of duty cycle. You cannot speak too much over a unit over a period of time. And in the US, we have other types of regulation. A single message cannot be on the air for too long. We have a hard limit there. Communication is also capacity-wise quite asymmetric. So you are going to be hearing more from the end devices rather than what you're going to be sending back to them. This is very important while building your use case because you have to understand that you won't be able to contact your device extremely often, and that's a good thing because it allows the device to sleep. But in general, you are going to be receiving more data than sending. Now, I've been speaking a lot about sending data, receiving data, but how does this actually occur in LoRaWAN? I didn't go yet into details. We have the concept of device classes in LoRaWAN. And the simplest class for communication is class A. In class A, it's very simple. The end device sends a message. This begins, let's say, the communication. The end device can send wherever it wants, but it can receive a message back only in two very specific time windows. The windows that we call RX1 and RX2, receive 1, receive 2. The idea here is that since we force the end device to listen only at those specific time periods, we can allow it to sleep. And sleeping is extremely good because it allows the device to preserve its battery. You can send something really fast, every 12 hours, everything else, you sleep, you maintain your battery for 10 years. Very efficient. Also very constrained, but depending on the use case, this is a very good match. Now, since you can talk to your end device only after it has spoken, there is high latency because, as I said, messages don't come that often. So what can we do to improve that in case we need it? The follow-up to this is the concept of Class B devices, where B stands for beaconing. Beacon here means that we will periodically have a small time window in which we can contact the end device. Outside of that time window, the end device may sleep, so preserving battery, which is very important. And it allows us to have a lower latency while contacting the end device. In general, the window opens about every 2 minutes, and during every 2 minutes, you may send a message to your end device. Other than that, it can sleep and preserve battery. The device that you see here on the screen, it's a water meter, but it's a bit of a more ingenious water meter. So instead of just collecting data whenever you want, so let's say every 12 hours, you can contact it every 2 minutes and request an on-demand reading. maybe because you want to close a bill or because you need an extra reading because you lost one in the past. It allows you to contact the end device really fast. Now, if 2 minutes is still too much for you, we have the concept of Class C. Class C stands for continuous, in which you may contact the end device at any time. This is the most battery consuming operation mode. In fact, it shouldn't even be done on a battery, but rather it requires access to continuous power, but it has the least latency. You simply can send a message anytime you want to the end device, and the end device will be able to receive it. The use case here in general targets, let's say, mass transmission. So you have a series of street lights that you would like to turn on and off all at once. The street lights already have power available to them, so the battery consumption is not a concern there. They can listen all of the time, and you may turn all of them on and on at the same time. Very efficient when it comes to transmissions. Now, going back, we were talking a lot about how we cannot transmit a lot of data. So in an internet world, we have this very developer-centric view in which we send a lot of text messages. A lot of text messages that we format in JSON. We have field names in there. They are very easy to read, if you've seen a couple of them before, that is. But it's not necessarily very efficient. A JSON message has a lot of, let's say, redundant information attached to it, and it makes the messages really big. We cannot really, or rather shouldn't use this over LoRaWAN, because the bigger the message, the more battery you're going to use. Instead, what makes LoRaWAN stand out is the fact that we compress the messages. We make them as small as possible in order to ensure that we use as little possible power while transmitting. This enables us to actually to have very efficient battery lifetimes. So in the case of, let's say, a temperature reading, while we would be used to, let's say, having this in text, the text that says temperature is 2542 Celsius, we can actually just encode that as a binary number, and we only have to spend 2 bytes, which is very efficient. Now, this doesn't mean that all of our platforms are going to have to speak with in binary, but what goes over the air is going to be very efficiently and tightly packed. And sometimes you may even skip the payload itself. So in the case of, let's say, a mousetrap, you don't necessarily have to say that it has sprung. Simply the fact that you've sent a message, an empty message, can mean that you have the trap itself has been triggered. Now, onboarding an end device, so this preceding step before you can actually do communication, requires a number of parameters. A number of identifiers, we call those UIs, device UI and join UI. It requires the root keys, the keys which are going to be used in order to secure the communication. We are going to need some information about what LoRaWAN version the end device uses, over what frequencies. And finally, we want to actually have a small script, a bit of information that tells us that binary payload actually means temperature is 25. A script that can translate between binary and humanly readable JSON. That's a lot to ask for onboarding. If I want to onboard 10,000 end devices, I don't want to fill everything here, all for every single each end device. So while this is something that you would be asked to input, all of those identifiers, and this is something that is, let's say, quite error-prone because you can get one letter wrong and it's all done. What we propose instead is the idea of device profiles, and those are LoRa Alliance-endorsed profiles which specify the parameters of the end device. And this lowers your surface of error because the only thing that you will have to do is input some identifiers, and you're good to go. The rest of the information comes from the well-known model. But even that's too much. I'm still asking you for too much when I ask for those identifiers, and that's something that we can optimize even more. So let's say QR codes. Because we would like to have the onboarding to be extremely easy, extremely fast, we shouldn't ask the users to input this information while they are trying to onboard their end device. And while doing so, we came up, in the Alliance, we have the concept of device identification QR codes, technical recommendation 05, which allows us to compress all of the information that I mentioned before into a QR code. And then you don't have to input anything. You just do what you're used to. You scan the code. And this is very fast. I have a video showing that. Device onboarding, in this case, it's using our product, but other vendors provide exactly the same experience as well, because the QR code is standardized within the alliance. You are greeted with a picture of my colleague. He scans the code. All of the information has been inputted from him, and you're good to go. All that he has to do is maybe to input the brand of the end device, and that's all that he had to do. Everything else is filled in for him already from the QR code. So provisioning is really fast nowadays. Now, how did we actually know all of this information about the end device? How did we come up with the profiles? This is something that we, at the Things Network, we call the device repository. It's an open source repository which contains those profiles for end devices. It is open. Device manufacturers actually input those profiles, and anyone else actually can contribute them if needed. If you have an end device and you would like to add it there for ease of use, you can contribute this yourself. Other vendors use them too. So for example, the Helium network also is based on this. ChirpStack will also have soon support for this as well. So it's an ecosystem-wide effort to actually simplify device onboarding. And it's open source. So we did the registration. We actually are pretty much done, at least from the use case perspective. We have our data, so we have the binary data that we receive from the end devices, those zeros and ones, or rather hexadecimals. And because we know the device profiles from the device repository and the payload codecs, we actually can turn the information that is binary, we can turn it back into a humanly readable format. So in this case, I have some LEDs going on and off, some battery voltages from certain devices, digital outputs, temperature readings. All of those things are just enabled by what exists right now in the LoRaWAN ecosystem. Everything open. But outside of just having all of this information, all of the data, let's say, we are also interested in something more. We would like to monitor and to understand how our LoRaWAN networks work in real time. We will want to see, let's say, which gateways are still online and which are offline. What type of usage do they see? Is there interference? How is the signal there? And for that, what you will be interested in is a form of monitoring. A way of doing this that we propose is the Network Operations Center. The Network Operations Center allows you to see historical data about the traffic that goes through your gateways. The idea here is to allow you to see, okay, I am no longer receiving messages, or I'm missing some data. What happened during that period of time? You can start to drill down into what happened in the past and work from there. In the case here, as part of the screencast, I'm walking through gateways and I'm looking at traffic rates. This is what this graph represents, packets per second over time. And I can also see how the packets are spread over each channel, over the communication channels. I can also see that the signal is really good. I can hear packets which are really far away. And I can also see clusters of packets in case some channels were really highly used at one point. So always keep in mind that you should be monitoring your LoRaWAN solution. It's not just about getting data from one place to another. That's the happy case, but it's not always that happy. In the LoRaWAN, since we use a shared medium, radio, there can be collisions. There can be other use cases around us that speak at the same time with our end devices. There can be problems with the forwarding devices, with the gateways. Maybe they lose power, maybe they lose internet. There are many moving parts. And the moving parts are there in order to simplify what you have to do for an individual device, but you should keep in mind that you need to monitor the moving parts. Now, back to end-to-end solutions. We have registered the end device. We are translating the data, decoding it. We have the data. What do we do with it? We are collecting data from 10,000 sensors. Well, the simplest thing that you can do is you can build a dashboard. This is the most common use case for data collection. You have some temperature sensors in the field. You want to see how the temperature advanced over time. This is, for example, what you see here in this particular dashboard. Over a year, how a temperature has changed. But you can have even more information. So you can check how the battery, what the battery status is, if it's draining, how it has evolved over time. You can check humidity. So let's say the last known value for all of those things. But dashboards are not everything. Dashboards are very good when you start, when you want to see that everything is working, but dashboards are only a tool that allows you to react. A dashboard, you look at it, you gain some information, you see some historical context, but you have to look at it in order to take an action. So what I'm proposing is that we shouldn't focus necessarily only on the dashboards, on visualizing data, but rather that we should think more, and we should think in automations. And this is what I'm proposing next. The idea is that since we have collected the data, we can also interpret it, we can process it live even, and we can start generating actions. So for example, we have this temperature sensor that verifies an industrial process. We have a set of a lower bound and a higher bound within which the temperature should be. If we go outside of that boundary, we can actually raise an alarm. We can send a physical person in there, or at least we can start signaling that something goes wrong. This is very important for compliance reasons. You are very much interested in case you need to keep, let's say, a vaccine at a certain temperature. I wouldn't know where that came from. You are very interested in ensuring that the temperature has been stable. You can also generate reports, again, generating them automatically. So let's say we have the water metering case. We want to generate automatic bills from it that we report by email, also very common, or in general, just the temperature at which we keep food in restaurants, again, for compliance reasons. And since communication goes both ways, we can also do automatic maintenance. So let's say every 24 hours, you want to clean up the ice cream machine at McDonald's. You are interested in doing that, so you want to turn on a valve remotely. You turn it off, you start the cleaning cycle. Once again, you hear back that the cleaning cycle is over, you can turn it back on. You can have all of this automation on top of LoRaWAN and using the device classes that I spoke before. And this is already more useful than just having data visualized, because you no longer have to look at the dashboard and then take an action, but the action is taken automatic. But there is still a bit more to it. One more step that you can do is to look at the concept of digital twins. So while we were building the dashboards before and building our automations, we abstracted away a lot of information. We knew that the sensor that had a particular name reported the temperature, where that sensor is, where is it mounted, what does it do. We abstracted away everything there just to focus on the main use case. But since there is more to it than just a temperature and an identifier, the sensor is in a physical place, it has a physical presence in a room, it's mounted somewhere, we can actually go back and build a digital clone, a logical representation of the sensor and of the process that it operates. This allows us to add back semantics, add back meaning to the data that we are collecting. So we go back from the dot line that you see while building a graph. You go back and you see, okay, where did that data come from? What is near the sensor? What other operations are occurring in the room? And this allows you to put more context into the readings that you're having. And this is enabled by digital twins at heart, adding more meaning back into the data that you're collecting. It also allows you to understand better how your processes are going, because you add back the physical context to it, the positioning, the room topology, all of this information that, in general, we abstract away while building, let's say, reports or dashboards. And this is the other end of end-to-end. We started from the end device, and we ended up with a digital twin of my boss, Johan Stocking, which is very cool. OK, so this was the main information that I wanted to share with you today. I spoke a bit about the end devices, the ecosystem, components that you see in the ecosystem. Are there any questions? I was either very clear or not at all.
You were super clear.
No in between.
And because I do have a question for you.
Please.
So on the dashboards for the network, what typical issues or surprises do you get when looking at these dashboards? Yeah,
let's go back to them a bit more. So one back and one forward. So the idea is that in, let's say, a Wi-Fi world, it just works when it works. But the idea is that radio, it's a shared medium. When I speak, everyone in the room hears me, everyone can speak over me. Well, not now, but if I didn't have the microphone, you would be able to. And all of this communication can be interfered with. So for example, if we have a lot of concentration over a small number of channels, of communication channels, this is not something that's visible here, but you would imagine that it basically, the color becomes darker. Those channels are very, very used. Because they are very, very used, it's quite likely that we may end up speaking at the same time, and then the messages may get lost. So what you can do from the insight that you have over here, like this cluster over here, you can say, okay, we have too many, those channels are used too much. We can actually choose to do communication over other channels in order to avoid the highly used ones. This is the kind of insight that you want to see. Also, well, when this loads back again, you can also see the traffic usage over time. So here there is a small time period of about 2 days in which the traffic was lower. I know why, because I turned off an end device accidentally. But this is the type of insight that you can get. You can see a difference, a change from, let's say, the steady state, the normal operation, the happy flow of the system, and you can understand better what happened there.
So how do you recommend going from this dashboard to remediation? I have some number of devices. I lost a bunch of information, or I did not collect a bunch of information from those devices. Now I need to go back and start getting that information from the devices.
So,
How do you go from a dashboard to remediation?
So filling in the gaps you refer here in general, right? Well, it depends a lot on the use case that you're doing. So certain sensors, for example, they have buffers on them. So even though they send live data on a periodic basis, you can go, depending on your device manufacturer may make available to you a buffer of data. So you are gonna be able to see, okay, we have a gap in the collection. Let's say that this part here was missing, and you can request back this type of data from the end device. You can also have redundancy, so you can ask the end device to receive a confirmation for the reading that you're sending. I do not recommend doing that much. Please stay away from it. But you can also do, let's say, redundancy at application layer. So you can send the same message twice. The network can also do the same. It can enforce the end device to send the same message multiple times. You can have forward error correction codes. So basically, this would allow you in the future to rebuild past messages. This is something that can also be very, very useful. In general, if the end device is extremely simple, it just collects and sends, you're gonna need to be quite careful. There is no going back. But if you have a more specialized end device that has a bit of memory, or at least the communication style is a bit more redundant, so we can build past messages from current messages, then you already have a way of recovering lost traffic. But they are forward-looking. So to repeat your answer, we can indeed, in a forward-looking manner, we can ask the end device to send more often, or to send the same message multiple times, to send it with more power, have a higher spreading factor, so making it available over a higher range. But this is something that fixes your problem for future messages. If you lost something in the past, you are interested in retrieving that somehow. It has 2 points. The terminology change itself is, it's something that occurred a while ago, but you still feel it. The app UI is the old name of the join UI from earlier LoRaWAN versions. At heart, in our UI, you're going to see it referred to as application UI for older LoRaWAN versions. So terminology-wise, it still matches. But in general, what you should be looking for is the manufacturer's advice there, what LoRaWAN version it has, if it's not on the device repository, and picking up from there. The function itself, it hasn't changed much. So if you just know it was an app UI in the past, it's going to be a join UI now, but that's pretty much it. You're not required necessarily to have a join server, or let's say a dedicated join server for a particular fleet of devices. Your network server provider most likely will give one to you anyway. And you can just register your devices there and you're good to go. Please.
So in Europe, there's
Yeah.
If you go like a large grid network or multiple continuous like Type-C devices, what techniques are there sort of on that those restrictions or the automatic windows?
So to repeat the question, the question was that in Europe, we have the duty cycle restrictions. I refer to them as not being able to transmit too much information over a period of time. The idea there is that if you would like to do a lot of Class C messaging, you would like to choose different channels. So if we go back to my Class C slide, you see here that this is the RX2 receive window. This one is done in a specific, using a specific frequency and a specific data rate, but it can be changed. Each end device can have a different frequency and a different data rate. So for example, you can use, let's say, a lower data rate if the devices are near you, near your gateways. That's something that can be done. You can choose another frequency. So the default frequency has 10% duty cycle, but you can shift it a bit, 200 kilohertz a bit to the right, and you're still within the 10 duty cycle limit. So there are tools available to you. The network can instruct the end device to basically not overlap itself too much in this RX2 window. Please.
Yeah, I'm not too familiar with the Things network. How does like the overall network coverage compare to some of the other public LoRaWAN networks that are out there? And are they interoperable?
Interoperability, it's about roaming. So going back to the Things network, we are very European heavy. People really like to contribute gateway coverage in Europe and to share it with one another. There is coverage in the US as well, but it's far less pervasive compared to what we have in Europe. So if you go to Amsterdam, you're going to be in the range of a gateway every 2 meters. That's very, very dense there. Whereas here, the more common one is Helium network. Helium has a bit of a different model of looking at how LoRaWAN should work, the economics of LoRaWAN should work. Whereas for us, it's let's build this thing together. You have the gateway at the end device, and we build cool stuff with it, at least on the Things network. On the, let's say, the development side of things, we are very cooperative. For them, they prefer a bit more of a commercial approach. So there is no roaming between us and them, but fundamentally it's the same standard. The same end device that works with us works with them, and the vice versa as well. Please.
Yeah, the Network Operations Center.
Yeah.
So is that a TTI?
Yes, so that's an enterprise feature in our case. This is something that is not available to community users because community users are not supposed to, well, are not really doing commercial operations. The idea behind the Things network is that we share gateways, we share coverage, we build proof of concepts or cool applications that can be used with LoRaWAN. But if you do it, if you have that mentality, you don't necessarily have an SLA to meet. You don't have a contractual agreement. It's all just friends, or rather building it together. So the Network Operations Center itself is meant to enable you to fulfill SLAs, to actually have some very specific KPIs, to monitor those KPIs, which is something that is not really in the spirit of the Things network, or rather is not required for the Things network itself.